Hi, I'm Joropo. I work at IPFS Shipyard, which will exist very soon, okay? That's a process. So I want to talk to you today about the thing like I wake up in the morning and I'm like, this has to change. The world has to change. People need to know about content addressing. I think many applications would benefit of lots of improvements if they could use content addressing in the workflow. And so I want to go through like, here's Bobby. He wants to make an app, okay? And he has a very usual problem, which is he wants to store medium size of data and a large one. The main way we're gonna see about it is like, hey, I have a profile picture. And it's on the edge of like, you could just send it in the request. That would work, but it's slightly expensive. Like now your RPC server has to handle the data, moving the full image. You probably want to use a cheaper CDN for that. There's no caching, so like if I update my bio, I have to refetch the image, which I don't like it. So usually the solution people come up with is, I'm just going to take my file and put it on the server and put the URL of the server. And I think it's not great. Like it works, but it has high coupling. Like now, if I want to change the server, I have to update my URL. And you think, oh, that's easy. I can just like write a migration. But like if this is not just an RPC server, but this is a smart contract, now you have to update the URL on all the smart contract. It does not, it's not very good. You should be able to do caching, and like there's ETag for it, but if you tried using ETag in the real world, it's slightly annoying, and not everyone get it right. And there's no horizontal security. Like if my CDN gets hacked, I can have very bad images on my website, and I don't want that. So I think the solution we should use is we should put hashes here. So this is a CID. This is the term we use in IPFS. It's basically a hash plus a tiny bit of metadata. And what does that bring us? So the easiest way we could think about this is I'm going to take my data and hash it. And that means that, and that already exists on the web if you want to use it in browsers. It's called sub-resource integrity. But I don't think it's great because it lacks many features that makes download useful. So the first one is like, if now I'm not just sending one image, but a video, the video could be very big. And due to the way the hashes work, we only have the hash at the end of the file. So if I want to download from the start to the end, I will only know if I got like 1 bit of data wrong, and I will only know that by the end. So if I download 20 gigs and I have to throw it all away, very bad. So what if we use like Merkle tree? It's a quite basic crypto construction of, instead of having the hash of the full file, I have the hash of this special thing on the side, which lists all the hashes inside the file. So we have hashes and offsets. And that means that like if my user 6 at a random point in the video, I can just download the topmost block, I verify it, I know that it's valid, and then I can jump in the middle and I don't have to download everything else. And that means incrementally verifiable, because as soon as like I get one of the blocks on the bottom, I can already return the data to my user. I don't have to download all of it. And okay, I just said we should use hashes because we can use content verifiability. But it's not the only thing. We have to couple it with something else because like I cannot contact a hash on the internet. It's not really a thing. IP works on internet addresses. So the usual, like a nice way to do it is to use DHT. The way we do is like, we have a bunch of nodes on the network that wants to figure out where files are. And so these are going to run DHT servers. And it's organized in a way where you sort them based on the public key. And then once I want to publish a file, someone will need on the DHT to remember that I have this file. And so I start like at a random node because I don't know the full network. And this random node will know some of its neighbors, and it knows less far away as you go farther. And so the first node will tell me like about a second node that is closer. The second node will tell me about third one, and the third one it doesn't know anyone better. That means that in this DHT key space for the particle CID, the node on the bottom right will be the one that has the file. And then when someone wants to fetch it, it comes later. It can start at a totally other different point in the DHT, and it's going to converge through a different path. It's going to find the same first node, and at this point, right here, the node remembers that the publisher stored this file. So when I want to download it, it's going to tell me, hey, you can go talk to the node that originally had the file. And it allows us to find us on internet to download files. And you might think like, okay, that's an extra thing I have to do, but we're already doing that in the previous example of location addressing. Even though we do it through DNS, we have like a similar recursive process. It's hierarchical instead of being based on the sorted key space. But it's similar. Like I asked various people, and they're gonna tell me at the end who has my data. So a last solution that we often see is indexers. And for example, on IPFS, we have IPNI. Torrent has tracker. So IPNI can work in that way, where the publisher sends to a PubSub channel a list of CID has, and the CID.contact, which is a database, is going to ingest it. And then later, the client can just ask CID.contact or some other indexer. And the point is, if you have a large amount of data, it's cheaper than using a DHT. And so at this point, like, we just did magic. Like, it doesn't look like it, but we really did magic, because now we can do many interesting things. So a random example I'm going to show of why I think this is superior. Torrent, for example. People tell you that usually, if you want to host video on internet, this is going to cost a lot. Like, a lot, because you have a bunch of transit costs and stuff. And I don't know, but like, there's a website with more or less legal videos, and they don't seem to have lots of money, and they work fine. And quite basic usage is that when the user downloads a video, they're going to reshare it with other people. So you can, that really helps you on the cost side, because people contribute to the cost of, like, I download a video, I contribute to the cost of downloading it because I will reshare it for the next people. It's more resilient because I can have thousands of nodes. And actually, Torrent is faster than HTTP in multiple cases, because like, I have fast fiber, very fast fiber. Europe is nice for that. And most HTTP servers are slower than my fiber. But with Torrent, I can just ask more and more and more nodes. And it can scale extremely well if the file is popular. And the first interesting thing to note is, like, thanks to the two properties of content addressing, which is I can verify my data, and I can I'm using the hash to figure out who I should contact, and I don't include that directly. I was able to download data from strangers on the internet. And if you want like the highest possible throughput between a few people, Torrent is probably the best solution you can have right now. Another interesting one is Git. So Git was created by the Linux kernel because they were solving the problem of, hey, we have hundreds and thousands of teams, and they need to talk about the code. And so the interesting thing that Git does is, because the Git, you have seen like probably Git hashes. I can show you one at the end if someone has questions, but it's a hash that points to a position in the source tree. And so if I need to share a bug with someone else, I don't need to say, hey, you need to check out the branch on this server at like this hour because I might modify it later. No, it's like a hash is fixed. It depends on the data. So if I would change it, the hash will also be different. And it's a really good properties because on Git, they don't have, on Linux, they don't have like one central server that everyone uses. There's a big one, big Git server, but also teams can decide, hey, I would rather have my branch be on GitHub, and I'm gonna pull it from time to time back to the main server. And like, it doesn't care how you got the data. It just, you have the right hashes, it matches, that's all I care. And so it's like really good property of, I want to talk about data. I shouldn't say, oh, but your data really has to come from like that server over there, and you need the valid TLS cert, and like, no, I just tell me what data I should have, and if I have it, it works. And the last application I found very good application of content addressing is Docker. Docker has like this problem of Docker images can get quite big, and most of the data is similar. And so using content addressing here makes caching very easy, because if I ask you about a layer, so Docker works in layers. So like I can start from a Linux layer. I can add the Go layer if I want to build a Go app. And then on top of that, I'm going to have a layer for my own application. And if I want to build like two different Go apps, it would be very annoying if I have to figure out that like, actually I can reuse the previous version of Go because the version matches and stuff. No, so you can do that very easy because you know all the hashes of every layer. And if the hash match, then you know the data has to be correct. There is no way for the data to be incorrect if the hash matches, unless you use a broken hash function, but we use Shadow56, and thankfully it is safe for now. And that means that you can deploy your own Docker caching layer somewhere on your data center, for example. And if you have many computers, it's going to be way cheaper than downloading it from someone else that's going to send it to you over expensive fiber. So interesting use case of like, hey, we have hashes that makes caching way easier. And so where does IPFS fit into that? I think the main problem with the free lattice solution I've talked about, and also content addressing solution, is that they're very snowflake. Like someone wanted to solve a problem, and they're like, let me make content addressing from scratch. And I don't think it's great because it's annoying for people to use. Like if I want to store my Docker layers on Filecoin, let's say, because I don't know, I heard Filecoin has cheap storage, it's going to be very annoying to do because I cannot easily, like Filecoin speaks a different language than Docker. And there's an opportunity cost in the same way that like, maybe the application that would work if we could have, I could take Docker and I could put it on torrent. Like that would be awesome. Like I would have peer-to-peer. There's this expensive Docker Hub subscription I need to fetch my Dockers. Like why can't I just fetch it from someone else that would happily reshare it for free to me? So if we were sharing like some basic protocols that we could all speak and work together with various implementations, wouldn't that be better? Like I would have Docker and torrent and I could do and mash them together and like, I don't know. But basically the point is, that's why we're trying to do IPFS. So how are we doing it? Primitives, important. So CID is the one I was showing earlier. It's a way to describe pieces of data. We write specs with the goal of multiple implementation having them supported. On my team, we do Boxo, which is a library for people to reuse and work in their own content address application. So again, like if you want to make your own content address application, you shouldn't have to restart from the beginning. I don't think it makes a lot of sense. So we have libraries. There are other people like Iro and Nabu, or I don't know the list. And so the last thing is actually getting stuff into web standards, browsers, and other applications. So there's like a huge difference between I can write a patch for a browser that works, but getting it merged and adding new features is a completely different process. It's very hard, and we have people that have experience to that. So we're really trying to change the world in the sense of like, kind of, you could say it's a bit limited, but I think the applications are pretty good. And so why don't we have IPFS everywhere? If we like, that would be good. I could have faster downloads, cheaper storage. Why doesn't that exist everywhere? I think the main issue I heard about the time is like trade-offs. And it's interesting of like, you don't need to be better, but you could be way better on other points, and I still gonna hear people tell me, oh, but like in that point, you're slightly worse. So it's kind of like a thing. I don't see any reason why just using IPFS, we need to be slower than other things, except no one put in the effort to do it yet. So HTTP is faster. Well, now we have HTTP on IPFS. If you like HTTP, there are various specs and issues of specs we want to write that could help you on that. But torrent is faster. Iro has showed up pretty good numbers that they are at least just as fast. I have some piece of code, soon TM. I don't have, I need to work on it, but it takes lots of time. So the browsers is like a huge piece. And it's interesting to work on adding support to browsers, but this is a long effort. And like, even if that happened, you sometimes often want to use new features. So why do you have to wait like for a new feature to show up? Can we just not give you the thing directly in the browser? So there's Kilia, JavaScript implementation. And you would be surprised of like how much Go and Rust code can be compiled to WASM and run in the browser. This is very good. And like the thing I probably heard the most is that IPFS is like a resource hog. And I would say like, no, it's not. It's Kubo is a resource hog, which is Go IPFS, which is the main experience a lot of people had with IPFS. And if you try this other somewhat IPFS implementation, you're gonna find that like, no, it's fine actually. A last thing I would say is like what I think is missing. There's this new implementation which is called Iro. It's pretty good, I hear. The implementation is great, but they stopped being intercompatible. And I think we could have quite easily intercompatibility with Iro, not with all the protocols, but make me be able to fetch and receive Blake free. So the protocol for Iro is some stream request response, and that would map very cleanly over the trustless gateway API specs that we just wrote and shipped in Kubo. So that would be nice if like, then other applications, then IRO would be come back in the IPFS ecosystem and be compatible with other storage layers. And I have a list of good reads if you want to hear more about it. And I was thinking, as a conclusion, like, I think it would be cool to show, hey, we should make an IPFS implementation right now. So I'm gonna do like the most basic thing, but a bit of live coding. Yeah, I tried doing something more complex, but it didn't work. The demo code was not on me. So let's try something. I'm gonna try to verify files from IPFS, and I think we should be. Oh, it already exists. Is that good enough? Okay, a lot better. Well, I'm gonna call it F. So the goal is, hey, I want to fetch data from IPFS in like few lines of code that's possible. So basic go, oh, need to. How do I make that go away? Okay. So I'm not going to bore you with the details. Sorry, it's Go. So the first thing I would use is a thing I just wrote. It's not merged yet, but it's going to be soon. So we want to use the new gateway API because it's very cheap and easy to use. So, oh, I see my LSP is not working because thanks. So what if, so I'm going to create a new client because I need a client to download thing. So, okay, really, my LSP really not working. I really have to think about it. Oh, now LSP. Okay, I needed to save. Great. So I'm going to use a static gateway. I tried doing the content routing with the DHT earlier, but DHT is not happy on that network, and I don't know why. So we're going to cheat a tiny bit. So I'm going to download from IPFS.io, but it's still going to be trustless and verified. So if IPFS.io were to lie to me and send me bad data, I will catch it. So I have a client now. I need to check errors, and as you know, if you return Go, checking errors is annoying, so we're just gonna handle the error. It's handled now. Now I want to get my file. f.download. Oh, client, sorry. I need to parse it. CID must parse. I have some other CID I meant to try. I should have it somewhere. Where do I have it? Oh, I know where it is. Sorry, it's gonna Tmax attach. Yeah, right here. That's, oh my God, it's not full. Tmax is making it annoying. Okay, great. That's the CID I wanted to try with. So I can be back right here. So because it's Go has types, so we use types because pretty good. So I just need to convert, like this is the string representation of a CID, and I call must parse on it, which will parse it. So must parse, it's called parse, but it will panic on error. And parse, oh my God, yeah. And parse called parse generic, which is gonna implement, it's gonna do multi-base. So, yeah, that's the magic thing. Okay, we don't want to look at that. The thing it's gonna do, it's gonna figure out that, oh, I gave it a string, and it's not /IPFS/, and then it's gonna look at the first character. That's gonna tell it the multibase. Once it decodes the multibase, so once it figures out the multibase key, it's gonna run it. This is base 32. And once it parses the CID, it's gonna extract 4 fields. The version, which is gonna be 1. The codec, which YBay, I think that's UnixFS file, DACPB. And the hash function, and lastly, how it's called. The hash function, hash length, and the actual hash that we want to verify. So handling errors, don't write, you should do something better with error, but like, I'm not gonna do it, so. We need to call close because this is gonna be a streaming thing. And lastly, we want to do io.copy from to os.std out and file. And I don't have OS. Let's need it. So great. So now, hopefully, if I'm lucky, I do go run, I pipe it into FFF play, and it should show up. And it didn't because, my bad. HTTP, oh no, NZ. yeah, I have proxy on this, and like it's not working right. And now, hopefully, there's like a 10% chance it works. No more. Oh, it loaded. So it's been a thing we're trying to do with Boxo of having it way easier to use and do the stuff you care about. So Boxo is like organized in various puzzle pieces. And like the puzzle pieces I just use is Feather, which implements UnixFS in a very lightweight. And it's streaming, so we can see that I don't have downloaded the full file and that I'm able to see the video. And so it's kind of one of the things that's like important is you want to have great tooling for users. And I think this is on the, like this is good enough for most people. Maybe I'm wrong. If you think I'm wrong, tell me. But like have this basic, quite basic interface. I create a client because of boring Go stuff. I need to have a place to put variables. And after that, I'm just, I do the thing I want to do. So I want to download a file, client.download file. And not all of Boxo is like that already. But we are aiming at making it better. We improve it all, every day. The gateway, for example, in Boxo was a huge part of the work while we also did the gateway specs. And so it's the end. Does anyone have questions? Steve.
Thank you. So Feather, I'm assuming this is doing verified retrieval, and does it have the ability to support multiple gateways to pull from to get more of the BitTorrent experience you were referencing?
So if you ask me in like a week, it will. Right now, you're right, it doesn't. But it's not the very hard part. Like I can, this is going to be hard to read, but the Feather code is basically, there should be a read method somewhere. I just passed it. So supporting multiple gateways is not that hard. We can have like a basic check of if a gateway is not working, I just switch one. You can also run multiple gateways in parallel and take the blocks from the fastest one. The hard part is like if you want something that's both efficient and fast, this is hard to do. But I think we should have something like that's 95% of the way there in Feather. And the main point of Feather is that it's very efficient. It's very light. Like the whole implementation is 300 lines of code. And I write lots of lines of code. You could make it way shorter. So I hope it answers the question.
So I hope I'm in the right talk, but this was why IPFS content addressing is the second best thing. What is the first? Is that Feather?
I don't know about the first. The point is you can decide yourself. You have to be creative.
Sweet. Okay, thanks.